sometime in the near future, the cryptographic math that protects your bank accounts, medical records, and private messages will simply fail. Security experts call it Q-Day, the theoretical moment when a powerful quantum computer becomes capable of shattering the encryption standards guarding the modern internet. The only permanent solution is to replace current algorithmic encryption with a system grounded in the laws of physics. In a quantum network, the simple act of trying to secretly observe or intercept a signal instantly alters and destroys it. It is physically impossible to eavesdrop on the data without leaving a detectable signature behind. For over a century, the phenomenon powering this, quantum entanglement, was restricted to perfectly isolated laboratory environments. The idea that two particles could be linked across space was so bizarre that Albert Einstein famously dismissed it as spooky action at a distance. But to secure global communication, physicists had to take this delicate quantum state out of those sterile lab chambers and force it to survive the noise of the real world. Building a perfectly shielded quantum network from scratch isn't a practical option. Laying thousands of miles of dedicated fiber optic cable beneath every major city on Earth would take decades and cost billions of dollars in infrastructure. To make this technology viable, engineers realized they had to pull off a specific compromise. They needed to send sensitive quantum signals through the exact same commercial fiber optic cables already buried under our streets. The problem is that quantum information is famously fragile. A single stray photon of noise or a slight temperature shift is enough to destroy it. The classical internet, meanwhile, is dense and relentless. The cables already in the ground are actively pumping billions of high-powered photons per second to carry everything from streaming video to financial data. Trying to transmit an entangled quantum state through that existing commercial traffic is like trying to whisper a secret across a stadium during a loud concert and expecting the person on the other side to hear every single syllable perfectly. Yet recently, research teams proved this is possible. In a landmark experiment, engineers successfully fired entangled photons through 24 kilometers of active commercial cables directly beneath the streets of Chicago, all while ordinary internet data was flowing through them. The first survival mechanism they deployed is a technique known as wavelength division multiplexing. This is a method of strict frequency separation operating inside a single strand of glass. They took the high-powered flow of commercial internet traffic and constrained it entirely to its usual optical spectrum, a congested frequency range known as the C-band. Then they pushed the fragile quantum signal into a quieter, separate section of the optical spectrum called the O-band. Like two radio stations broadcasting on different frequencies from the same tower, the signals stayed in their own lanes. But keeping signals from drowning each other out during the journey only solves half the problem. Surviving the trip means nothing if the receiving station cannot accurately identify the signal. When that quantum information reaches downtown Chicago, the receiver faces a specific challenge. It has to identify the arrival of one single individual quantum photon amidst the background of internet noise. To catch it, the team relied on a second mechanism, a precision timing system originally developed for particle physics called the White Rabbit Synchronizer. This device functions as an atomic-level stopwatch. It aligns the clocks across the network down to fractions of a billionth of a second, telling the receiving station the precise instant to look for the photon. When that exact fraction of a second arrives, the photon is registered by superconducting nanowire sensors. These microscopic detectors are cooled to temperatures near absolute zero to eliminate thermal interference from the outside environment. The combination of these systems allowed the team to measure an entanglement fidelity of 94% across 24 kilometers of active commercial traffic. This result proves that the rules of quantum mechanics can survive the chaotic reality of modern city infrastructure. The economic implications are concrete. Since quantum networks can piggyback directly onto the wires we already use, the timeline for a rollout is determined by hardware deployment rather than the slow process of digging new tunnels. This realization has accelerated global investment. China currently operates a 2,000-kilometer quantum communication backbone stretching from Shanghai to Beijing, which is already used by approximately 200 government and financial personnel. To avoid falling behind, both the United States and the European Union are now deploying their own national blueprints, aiming to stitch together research hubs into secure quantum backbones. Industry analysts project the combined value of quantum technology could reach $2.7 trillion by 2035. This projection is driven by the immediate security needs of sectors like banking and critical infrastructure, where the cost of data breaches justifies the high price of specialized quantum hardware. Global powers are treating this as a long-term strategic priority. The goal is to establish a communications infrastructure where security is a fundamental property of the physical medium, rather than a layer of code that can be bypassed. While much of the focus is on a global race, this transformation is happening block by block in the physical world. In addition to Chicago, researchers have recently successfully linked entangled quantum signals across nodes in Manhattan and Brooklyn. Integrating this technology will be a phased process. It is appearing first in high-value, high-security sectors like banking and defense before it reaches mainstream consumer applications. While today's internet relies on digital encryption, the first components of a network secured by the laws of physics are already operating inside the cables beneath our feet.